This is February March 2024, 0625, paper 42. Let's start with this question. So this question is, and by the way, if you want to get an A in this paper, you most likely need to get at least 45 out of 80. And to get a B, you need to be more than 35, and to get a C, you need to be more than 26. Now, be advised that this is an 80-mark paper. Now, I believe you should be able to score at least more than 50 points or 50 to 60 marks in this paper. It's not that difficult. But anyways, that's your target. If a speed time graph is given, he says describe the motion of between 0.9 to 2.9. So it's going to be somewhere around here to 2.9, 0.9 to 2.9. So it's going to be somewhere around this time. So we can see that the speed of the object is not changing, right? So since the speed is not changing, we can say it's moving at a constant speed. Another way to look at this would be to visualize the gradient. You see, the gradient of speed time graph represents acceleration. So if the gradient is 0, then the acceleration is also 0. And if the acceleration is 0, that most definitely means that the object is moving at a constant speed. The next part, he says, describe between 2.9 and 3.5. So between 2.9 and 3.5, we can see that the speed is decreasing because as the time is passing by, the velocity of the object or the speed of the object is decreasing. So we can say it is a deceleration case. And since it's a straight line with a negative gradient, we can say it's a uniform deceleration. Similar for the last point, 3.5 to 4.5. We will say, 3.5 to 4.5 is this region when the speed is 0. So we can say it is at rest or it is stationary. I've added these words for you before solving the question, or instead of me writing this, it saves time and effort. So these words are already there. Similarly, you will find the definitions being already there in this question, because I'm here to discuss how to solve the numerical parts and how to discuss the theoretical parts. Question number part B1, he says that brakes are applied, bus traveling at this speed, brakes are applied, constant for 23 meters, mass is given. So he says, calculate the kinetic energy, which is going to be very straightforward as 1/2 mass into v square. Please be advised, write down the formula, then replace every value in its appropriate place. This way, the examiner knows where you pick the values from, and don't forget to square. When you do that, this answer is going to come out as 7.1 into 10 raised to the power 5 joules. So this will be 7.1 into 10 raised to the power 5. Now be advised, if you don't write that unit, you don't get that A1 mark or answer mark in the marking scheme. The unit needs to be there. Calculate the force required to stop the bus. So the question originates from the idea that this is the amount of energy the bus already possesses. So if you want to stop the bus from moving, you need to remove this energy from the bus. And the best way to do that, would be to stop the bus by applying brakes, and to remove this energy somehow. So if you apply the brakes, you're slowing it down. So you're removing the kinetic energy until it has 0 joules of energy. So work done is equal to force into distance. Again, this is a common part, repeated part. No need to fret about this. So this will be 7.1 into 10 raised to the power 5 equals to force is what we need to find out, multiplied by the distance traveled. So he has mentioned that he tries to stop within 23 meters. So it means that it will take 23 meters to finally come to a stop. So this will be 23. So how much force do I need to apply so that this much amount of energy can be removed from the system within a distance of 23 meters is the question. So force will come out as 30995 newtons, which will be, of course, rounded off to 3.1 into 10 raised to the power 4. I can't leave my answer like this. I need to write down newtons as the unit for force. Question number 2, define impulse. It's the product of force with time duration it is being applied for. So this actually comes from the idea that force is actually equal to delta P, or change in momentum, divided by time. If you bring time over there, this becomes F multiplied by change in time equals to delta P. This whole multiplication, force with time, is actually what we call as impulse in physics. So that is why it is necessary to mention there is a product of force and time for which it was being applied for. Now, question number 2 follows the question of a rocket. It's a very repeated question. He says that we have a velocity of a gas being emitted at 1400 meters per second at rate of 28 kg per second. And he wants you to show that the force is 3900. Now be advised, If you are unable to solve the part that represents show, no need to worry about the fact, because this value will be used somehow in the next part. So if you're unable to solve this part, don't leave the whole paper. Please continue for the next part and use this value for the next part. It will definitely be used. Now, we want to find out the force. So let's write down force equals to change in momentum divided by change in time. If you open the change in momentum up, it looks like that this will be mass into change in velocity divided by change in time. Now, if we go back to the question, the velocity is not changing, but we are definitely losing mass somehow. So I will change this equation to fit this situation by this. So change in mass divided by change in time multiplied by velocity. Now notice, why am I writing mass and time separately? Because I can see that kilograms per second, which is mass, which is kilograms divided by time or seconds, is given to me already. So that's why I'm using it separately. And I'm doing this for you. Otherwise, we could have directly multiplied 2800 with 1400, because when we say 2800 kilograms per second, it means that this is actually being divided by 1. The time is 1 second, because when we say per second, the per means 1. So very straightforward. The value comes out as 3920000 newtons, which definitely can be rounded off as 3900 kilonewtons. So we've shown the part. It says calculate the maximum mass this force can lift from the ground. You see, the maximum force this force can lift for you should be more than, of course, the mass of the system. But let's see how much this force can do for us. So since we're going against gravity, so the force should be equal to or should be greater than the mg. So force is 3.92 into 10 raised to power 6. Again, I'm just using 3.92 to be on the safe side. I could have used 3.9 or 3900 kilonewtons. It's totally fine. Equals to mass, which I want to lift against the gravity of 9.8, right? So mass comes out as 400,000 kilograms, which is going to be 4.0 into 10 raised to power 5. But again, don't miss out the unit, which is kg for mass. He says a car has a weight of 1300 newtons. The car is supported by 4. Again, it's a classic question. You will find the same question in MCQ with an example of an animal. That an animal is standing on 4 feet, generally elephants. So how much pressure is being exerted? So no problem. So pressure, don't forget to write down the formula. Pressure equals to force over area. You have to identify where the force is coming from. And we understand that the weight is also a force. So sometimes he will give you the mass, which will be converted using mg as an extra step, but it's already been done for you. So 13,000 divided by the area, which is 0.016. Now be careful. When he says each tire, this means that it is one tire. Now the car has 4 tires. So this will be multiplied by, or the cross section here multiplied by 4, because it is being distributed on 4 different tires separately. When you do that, your answer comes out as 2.0 into 10 raised to power 5 pascals. So this will become 2.0 into 10 raised to power 5 pascals. He says, explain in terms of particles why air pressure in the tire increases when the car travels along the road. Now, there are 2 to 3 points you need to be careful about in these questions. This is, again, a classic repeated question. You see, we understand that the gas molecules are moving randomly. Now, since they are moving randomly, why increasing the temperature, or what happens when you increase the temperature? You see, he says that the pressure increases, but we don't know why. Now we do. You see, the temperature is directly proportional to the kinetic energy, which is directly proportional to the speed of the molecule. When you are moving on the road, the friction causes the tire to heat up. When the tire heats up, it heats up the air molecules. When the air molecules are heated up, when their temperature increases, their speed of movement increases. Now, why does that matter? You see, for force or resultant force, we have change in momentum divided by change in time. What you are doing effectively is mv divided by t. Now, You're not changing the mass of the gas that is inside the tire, which is primarily made of nitrogen, oxygen, carbon dioxide. You're changing their velocity. You're increasing the velocity because you're increasing the temperature, which is increasing kinetic energy. Kinetic energy is half mv square. We can't change the mass, but you can change the speed, or the change in speed is observed as the kinetic energy change. When they have more energy, kinetic energy, they have more speed. When they have more speed, they have more momentum. If they have more momentum, when they collide with the walls of the tire, inside the tire walls, definitely they will be exerting more force. Now, pressure is force over area. You can't really control the cross-sectional area of the gas molecule that collides inside the tire pressure or the tire walls. But what you have done is increased the force they collide with the walls with. That's why the pressure increases. This is exactly the whole thought process we're going to write down in English. So the friction between the tires causes the temperature to increase. This is where the whole process actually starts from. This is the starting point. This causes the speed of the molecules to increase, leading to a greater change in momentum. This is what we're explaining in terms of maths. As the molecule collides with the walls, this leads to higher change in momentum. Again, this variable. This produces more force, which is again this variable. More momentum, more force, or more change in momentum produces more force, and more force causes a change in pressure. This is why increasing temperature increases the pressure inside a container. This is a very long explanation. We had to do it because it was a 4-mark question. It has to be appropriate. A gas cylinder contains a gas pressure at this volume initially, at this pressure initially, the volume of this much initially of compressed gas. He says that each balloon, he's trying to fill in balloons. So each balloon contains this much amount of volume of air, but at this pressure, the temperature remains constant, which means he only wants us to think about Boyle's law, which is pressure inversely proportional to volume, which of course becomes P1 V1 equals to P2 V2. This is what he wants us to think. Calculate the maximum number of balloons. It's a good question. It clarifies many misconceptions. You see, one side represents the initial situation. The second side represents the final situation, or another situation other than the initial situation. In the initial situation, I can see that this is the pressure and this is the volume inside the container. So let's write these values down first. So this will be 2. And you turn this to power 6. This is what I have, or this is the amount of gas I have inside the container before I've started filling the balloons. The balloons, however, end up having the atmospheric pressure. So every balloon that I'm going to fill in, or whatever volume of air I fill in the balloons with, this V2 inside the balloons, will be at an atmospheric pressure, or will be at a pressure of 1 into 10 to the power 5. Since we've memorized this is the atmospheric pressure value, that's why I've referred to this as an atmospheric pressure value. Otherwise, you could not have said that. It would be fine. And this is going to be V2. How much volume would I have if I let this gas escape from this pressure to exist at this pressure? How much volume of this gas would then be? So volume of V2 comes out as 0.52 meter cube. So if this gas was allowed to expand freely and go up to atmospheric pressure, or 1 into 10 to the power 5 pascals, it would expand, or it would occupy a volume of 0.52 meter cube. One balloon needs 0.015. So when it comes to number of balloons, it would very straightforward be 0.52 is what we have available at atmospheric pressure if allowed to do so. And we want to fill in 0.015 meter cube of air in that balloon. So if you divide this, this comes out as 34.66. Now this is again a trick played by the examiner. We understand that if we try to round it off to 2 significant figures, this will be 35. This will be wrong, because here it's not about maths, it's about logic. When you fill in complete 34 balloons, you can only fill in 66% of the 35th balloon. He says maximum number of balloons that can be filled completely at this pressure. So we would have to round this number down to 34, because the extra part wouldn't be able to fill in an extra balloon to make it 35 balloons. So be careful that in some questions we don't have to pay attention, we don't pay much attention to the mathematics of the value, but rather the sense of the question itself. We can't fill in the 35th balloon, so we will settle at 34. Question number 4, define specific heat capacity. Thermal energy transferred to a substance. Now be advised that if you simply write down energy transferred, you will get just 1 mark. The reason I've highlighted this is that you have to write that it is thermal energy that is being transferred. per unit mass, per unit change in temperature. That's what is going to make it specific. Now, the word specific means that you're considering for 1 kg only. That is what is special about specific heat capacity rather than heat capacity alone. A volume of this oil is heated in about 7 minutes. The temperature increases from 20 to 180. The density of the oil is this much. The heat capacity is this much of the oil, I believe. Yes. Calculate the mass of oil in the pan. Now, this part only wants you to use the density is equal to mass over volume bit. That's what he wants to test in this part. So please make sure that you appropriately write down the formula, that is density is equal to mass over volume. We have the density over here. We have the volume over here. We can find the mass very quickly. So this will be 0.0024 equals to, multiplied by the density, which is 910, equals to mass. Mass comes out very quickly as 2184, but I think this will be 2.184, yeah. So this will be rounded off to 2.2, but if I leave it without a unit, I will be deducted with 1 mark. And only get credit for 1 mark. So calculate the energy required to increase the temperature. So the equation we use to do that is Q equals to MC delta T, which is a very straightforward equation. Since energy is required, Q is a representation of energy. So mass will be 2.2. C is the specific heat capacity given to me in the question as 2000 joules per kg degree centigrade. 2000 into delta T. Change in temperature is from 20 to 180, so it will be 180 minus 20. Now, if you write this down in the calculator directly, you might encounter an error. So please first take the subtraction. If you haven't added the brackets, if you try to solve this without the brackets, you will get an error. Please be careful. So this will come out as 7.04 into 10 raised to power 5 joules. So this will be 7.0 into 10 raised to power 5 joules. If you had to do this job with the oil to raise its temperature from 20 to 180 and its mass would have been 2.2, then this is the amount of energy required, either provided from a stove or either by burning wood or either by an electric heater. This is what is going to be required. Calculate the power required to supply. This is again a generic random question, not a random question, but a repeated question. So for power, we have energy or work done divided by time. Energy was found in the previous part, which will be 7 into 10 raised to power 5 divided by time. So I should have some time in this question. It was given to me, I think, as 7 minutes. Yes. So I want to achieve this target. I want to achieve this task of boiling, or let's say changing the temperature of oil from this point from 20 to 180 in a matter of 7 minutes. And the time is going to be in seconds. So that's why I multiply with 60. So this much amount of energy supplied in this much amount of time, definitely. So this comes out as 1676 watts, which is roughly joules per second. Watts is joules per second. So I need to supply 1676 joules for every second oil is on the stove. Only then I will be able to achieve the temperature change from 20 degrees centigrade to 180, provided that the mass is 2.2 kg. Provided that the heat capacity is 2000 joules per kg degree centigrade. This is where it all ties in. So I need to convert this into two significant figures. So I'll write down 1.7 into 10 raised to power 3, but since it's power, I'll write down watts. Moving on to question number 5. The table shows applications. Okay, fine. Now again, this is a classic memory-based question. I can't really help you with this. You just have to memorize where everything goes. So Bluetooth is generally falling in radio. Optical fibers, generally we use infrared or visible light. Security markings use UV radiation. Banknotes. Sterilization uses gamma radiation to kill bacteria on food or at least medical equipment. Wireless internet, which is generally Wi-Fi signals, are actually going to be in the microwave region. But not to be afraid by this. This wouldn't be able to heat you up, or you are not being heated, because we are generally familiar with microwaves heating our foods up. But this is very low power. It's not in the same spectrum. It's not in the same radiation level or the frequency that heats up the food. But anyways, a common misconception in this question, or an error, was he's asking you to state the appropriate speed of radio waves in air. The radio wave belongs to the electromagnetic spectrum, electromagnetic radiation, gamma up to radio. They all move at the speed of light. What some students did by mistake was they forgot to write 3.0 as two significant figures, and some of them, since they read speed of some radio waves, they thought that it's being speed of any sound or any other thing. They mentioned 330 to 350 meters per second as the speed of sound. It's a completely different thing. Be careful. So it says, show successive crests. What type of crest would it have received before crossing this barrier? So what I advise generally to my students is that I understand that the examiner has not said that this is drawn to scale. It doesn't matter. What we can do is place a ruler here. Whatever visualization you have, whatever scale you have, just take a measurement. Let's say this comes out as 2.1 centimeters. Good. So let's measure 2.1, then 2.1, then 2.1, and just make dots over here. This will help you to visualize the three crests. Sorry, it should be drawn exactly on the line. It will help you visualize three crests, and the diagram will turn out really nicely. So then you can just remove the dots, these dots, and you'll have a very nice diagram in which the spacing of these crests looks very, very nice in terms of the representation or presentation. If you choose to do it with the freehand, that's again your choice. I'm just recommending how to improve the presentation. In this part, he says a plane wave of same wavelength is being represented, but notice that the barrier has a much wider gap this time around. So it was this much here. Now it's this much. The gap is much wider. So how would that affect? You see, a general recommendation again from my side is that just draw a very light dotted line in front of the barrier where the wave will not be able to bend. And since you took the measurement of 2.1, let's say for the sake of example, 2.1, 2.2, whatever measurements you took, I would advise you to make those markings in this direction. So 1, then 2, then 3. Similarly, 1, then 2, then 3. And then make curves to come up to this dotted line. All the while making sure that the distance between these lines is not changing. Again, this has to be done freehand, or you can use a compass if you have enough time, like this. And the part where there was no barrier, these lines will be straight, like this. But please join them with a ruler, and ideally they should look like this with one single swift motion. But again, you have to be a bit scientific about that. And at the end of the day, what you can do is just simply erase the dotted lines or erase the dots, because they were there to serve you as a guide, because that's what actually exactly happens. The wave that is in front of the gap does not get bent, but only the wave that encounters the edge gets bent out. So this really helps you out in terms of drawing the wave. So shows, okay, same with incident, okay, fine. 3 successive crests of the wave after it passes through the narrow gap. So we don't have to draw any waves here. We only have to show what happens on the output or as a result of this. Okay. Moving on to the next question, we have question number 6. A full scale diagram. Now be advised, when he says full scale, it means measurements can be taken from this diagram for the next parts. He says, okay, fine. Right, principal axis is shown on the figure. A single ray to locate the position of the center of the... Now this is a repeated question in terms of lens, and it's a good question. You see, normally, wherever the lens is, we draw a straight line, and we draw a line through the optical center, which goes to the image. The straight line passes from the focal point and then goes to the image. So this must be the focal point. But since we're following the rules, this is what we're expecting. We don't have the lens over here to do that for us. Rather, we're going to find the lens ourselves. So the best position to, or the best way to do that is to draw a line from this point to this point, which is not entirely accurate. Use a ruler for this, definitely. So connect the top of the object to the top of the image over here. Wherever it crosses over to the principal or from the principal axis, you know for sure now today that this is where the lens should be. And definitely in the next part, he will say position of the lens, label this line as L. He mentions, and also Please don't forget to add the arrows. And then he says, determine the focal length. Now, you know that there needs to be a straight line parallel to the principal axis, and this line, then again, use the ruler for that, has to converge and meet at this point. So you place the ruler in such a way that it comes in line with this coordinate and this coordinate. So when you do that, you successfully have located the focal point, because it automatically crosses over only where the focal point is going to be. Don't try to force this answer. Follow the rules. Again, this will be with arrows, and this is your focal point. So the focal length is from the optical center up to the focal point. If you do that by a past paper printed at home, you might get a different answer, but the marking scheme says 2.1 centimeters. Now, be advised, if you have this paper printed by another past paper manufacturer or people who provide past paper practice booklets, you will find that their magnification is a bit off. You might find that this answer that you're going to get may be 2.4, 2.5, or maybe less than 2.1. When I printed this paper, I got an answer of 1.7, which is significantly off from the actual answer. But be advised, rest assured, the papers that you're going to get in your actual Cambridge examination, they will not have this problem, and all of your class fellows and peers, if you come out and discuss your paper, will have this answer on it. But definitely, this is the focal length that we're going to talk about. He says an object is the object is moved 2 centimeters closer to the lens. Now, this is where it gets interesting. So he says, we know for a fact today that the focal length is going to be 2.1. And if you take the actual measurement from this diagram, this is generally at 3 centimeters. So the focal point is at 2.1. He says it is being measured 2 centimeters closer, is moved 2 centimeters. So you're moving it 2 centimeters to this direction from its 3 centimeter position. Again, this has been done by measurements, which means that the object probably today, if this is my focal point, it was placed here somewhere at the beginning of the question. Today, it has been placed somewhere along this line. Now, we know that this is the case of a magnifying glass. And if you wanted to draw rays, we could have done that, and we will find that the light rays are going to be diverging on the other side. And the only way to find the image is to backtrack our way with dotted lines and find that this is my image. This is what the image is going to be. This is what the image has become now, because you moved the object beyond the focal point. And this is special for converging lens. This is a case of magnifying glass. He says 2 changes to the characteristics of the image. So this one was real and inverted because the arrowhead was over here, and now the arrowhead has been turned upside down. But this time around, it has become virtual because the choice of virtual is being on the same side as object and image, and it has been magnified, or you can say it is now upright. It is magnified. We couldn't have used magnified because this was also being magnified. This is also being magnified. So since they're expecting a change, so magnification is really not a change. That's why they're looking for upright versus inverted. Otherwise, that was perfectly fine answer. So draw a circuit symbol for the potential divider. We have that as a variable resistor or a rheostat, if for that matter. This is what a potential divider would look like with wires, right? It shows a circuit. This is a potential divider with 2 resistors in series with each other. Voltages will be divided. He says that we want to find the V out if R is 3 kilo ohms. Now, there are 2 ways to do that. Which method you choose to approach it from is totally up to you, but I would advise you to use the potential divider rule, which is whatever voltage or component voltage you want to find out, take its resistance in the numerator and divide this with the resistance of the whole circuit, which will be 1 plus 3 kilo ohms. So this is 1 plus 3. I'm not adding kilo ohms. Why? Because kilo is in the numerator and kilo in the denominator. When you eventually add them together, they will be cancelled out. Multiply this with the battery voltage, which is being shared among them. So this will come out as 1.5 volts. If you're not comfortable with this method, what you can do is simply use that they're both in series. First, find the current to do that. So this would be 6 equals to I into 4,000 ohms, because they're in series. 1 plus 3 would become 4,000. So the current is going to come out as probably 6 divided by 4,000. becomes 1.5 milliamperes, 1.5 milliamperes. And then you simply multiply this current with the resistance by using V equals to IR again. That would become 1.5 into 10 raised to the power minus 3 multiplied by resistance, which is 1000. This will become 1.5 volts once again. This will be 1.5 volts. That's completely your choice, what you choose to do with it. The value of I is adjusted again until the current is 1.7. Now he tells us that the current today is 1.7 milliamperes, so he wants to find us how much charge flows. So Q equals to IT, 1.7 into 10 raised to the power minus 3, because it's a milliampere question, we'll multiply by 300 seconds. The total charge that flows through would be 0.51 coulombs. 0.51 coulombs. The question number 8 is about the wire current. I have added an image how to use the hand to draw the magnetic field around the conductor. You see, the thumb represents the direction of the current, and the current direction is already given to you. Sometimes he wouldn't do that. Sometimes what he would do is add a battery on the outside circuit with no signs given to you apart from what the distance they have. So this is positive and this is negative. So the current is supposed to flow like this in that case. So the direction of current sometimes is not given. So you align your thumb with the direction of the current and you try to grab onto the wire in this fashion, in this manner, right? So in this case, and we are using the right hand grip rule for this. So the magnetic fields would look something like this, that they are probably along the finger, they're probably going in this direction, trying to grab this wire like this. And if you view this from the top, this is what the magnetic field lines would look like. They will be circular, but I'm not sure should they be clockwise or anti-clockwise. If you keep following the rule of this, the right-hand grip rule, you would realize that these all magnetic fields are going to be clockwise. Now, I would use a compass to do that, and I would start from the outermost line. I've done this for you before coming to this paper, but I would start from the last magnetic field, Y, because I would make sure that it follows all the edges. I haven't been able to do that very briefly in this paper, in this diagram, but I hope you can do that by using a compass. Place the needle at the very center and place your pencil end at the very edges and just check whether it crosses all the borders. Shift it slightly inward so that it doesn't cross out the circle, doesn't go out of the box. Draw this one first, this one second, and this one the third one. Why am I saying that? Because it will, this question will test your sense of space management. You see, why are we doing this? Why is it required? Because the magnetic field, if you observe, the distance between the conductor over here, the distance between the conductor up to this point, and the distance from the conductor up to this point, it's not a uniform distance. It's not gradually increasing. It's increasing non-uniformly. So the space between these two magnetic fields is much less as compared to the space between these two magnetic fields. And I've done this deliberately. And this is how we represent decreasing strength of magnetic field as you move away from the conductor. So as you move away from the conductor, you have to represent that the magnetic field strength is decreasing. And that is how it is. So in order to represent this, we represent magnetic field lines by increasing distance. That is why I'm telling you, or suggesting, that you start from the outermost so that you know how much space you're left up to the point you get to the center of the conductor. And then you draw this line, and then you draw the last one really close to the conductor, showing that the magnetic field is really strong when you're very close to the conductor. This is the way to draw the diagrams. Arrows, 3 circles, because he mentions 3 magnetic fields, and increasing distance. And if you don't do that, if you draw uniform circle distance, you will lose 1 mark from this diagram. Anyways, state how these changes. So it says the current in the wire is increased and the direction of the current is reversed. So the magnitude of the current directly affects the strength of the magnetic field. So the magnetic field strength, or the magnetic field, definitely becomes stronger, which means that if I had to draw this again, probably if it's with a cross, for example, it would have more lines as compared to before. If there are 3 lines, this one might have 5 or 6. Again, we can't see these magnetic field lines, but we will draw them accordingly so that we can show to the examiner that I know If current increases, magnetic field becomes stronger. And in order for me to show you that they have become stronger, I will draw more number of lines. State how these changes affect the magnetic field now, since the current is also reversed, the direction of magnetic field will also be reversed. So this time around, they will be anti-clockwise because I would be using the right-hand grip rule to the opposite direction. So the direction of magnetic field direction is also reversed. And if I might add, a better answer would be that they will now be anti-clockwise. And stronger, you should or you would write down that the lines are closer. Lines are drawn to be closer to each other as a representation. But again, since it's not in the marking scheme, I'm not emphasizing on that answer, but I would be expecting this in an answer of a person who is aiming for an A star or distinction. B part, electricity transmitted at high voltages. Again, a repeated question, repeated part. He says, explain why voltage increase improves the efficiency of the system. You see, if this is where you're producing electricity, and if this is your home, this is where you want to use it, chances are that there's going to be a very long distance between them. For example, the distance is up to, let's say, 10,000 kilometers, which is very far away. Now, if you were to transmit at low voltages, comparatively low voltages, then the transmission lines between the powerhouse and the transmission network is going to contribute to a significant loss of power. Because although the formula for power is V square over R, and we also have a formula as I square R, we don't talk about V square over R because there's a problem. The problem is that V would be the voltage or the potential difference of the wires themselves. And it can only be done if we have one terminal over here of the voltmeter and one terminal over here. This actually defeats the purpose. You see, if this is 10,000 kilometers, this will also be 10,000 kilometers, which again would not give us the right answer. And it's impractical. So what we've settled for is an equation that is P equals to I square R, because I can use a simple ammeter at the very start of the system, and I would know that the current received at the end is also the same. Why? Because it's a series circuit, and I know the current in the series circuit remains the same. Or you can argue that if, let's say, 10 ampere current was injected, it is equivalent to a certain number of electrons. The same number of electrons will be received at the other end. So we have a guarantee of the current in the wires, which is why we use this. It's more practical. So we want to reduce this current somehow so that P equals to I square R. When I use this formula, the power loss or the value of power comes as small as possible. But where does this resistance come from? Which resistance am I talking about? This is the resistance of the transmission line. This line is what I'm interested in. Now notice that you have already done the formula for resistance, which is resistance equals to rho L over A. If you increase the length, the resistance increases. If there is a high resistance of these wires, the power loss increases. Now the problem is that we can't really control the resistance of these wires. We can at the point of manufacturing, at the time of manufacturing, we can do that, but we can't do that again and again. Once they are installed for life. At least 200 to 300 years. For 200 to 300 years, they will stay there. So the only option we have is to just reduce the current, because that only invites changing the transformer in a physical sense. So if I have more number of turns on the secondary side, if I increase the voltage, the current decreases. Why? Because power is equal to current into voltage. If I'm demanding or if I'm producing a high voltage, same amount of power can be produced at a lower amount of current. And since power is a consumable item, we can't have an infinite number of power or infinite amount of power. This is what eventually happens at the end. The power is constant. We can't change that. This is, of course, coming directly from the generator. We can't change the power, but we can manipulate the voltage by using a transformer. When we do that, current automatically changes. We are deliberately increasing the voltage. So the current through the transmission lines, instead of being 10 amperes, maybe goes down to 0.5 amperes. If I reduce the current, I reduce the power losses, because I really can't control the resistance of these wires because they've been installed, they've been manufactured, and they are already there when new systems are going to be installed, or new houses, let's say, are going to be added in the same vicinity or in the same area. So we can't really control, we can, but it will require much more money for the sake of infrastructure. So explaining all of these problems, the economic and the engineering side of this, it will be that at high voltages, current of the transmission line reduces, keeping power constant. This reduces the power losses according to the P. Now, the problem is I can't really type I square R, so I've written I2R. So don't write I2R, write I square R. This improves the overall efficiency of the transmission system. Definitely, if you're losing no power in the transmission lines, if you send 1000 watts of power from the transformer, chances are houses will be getting 1000 watts of power, but definitely over a very large distance, it's not possible. If you're losing most of power in the transmission line, your houses, which actually do definitely need power, will get less here because most of the power is being lost in the transmission line as heat to the surrounding. It's not good for efficiency. Question number 9, he says, an experiment directly involving alpha scattering experiment. Classic experiment says, conclusion about atoms from the observation. So what was the observation? Most of the alpha particle went straight through. Simple, straightforward table, simple, straightforward answer. Atoms are mostly empty space. Some alpha particles are deflected between 90 and 180. Two more conclusions again, conclusions with their observations and explanations. Gold nucleus is massive. It is very heavy, is one of the conclusions. And why did we say that? You see, the repulsive force between an alpha particle and a gold nucleus, again, at the time we didn't know that there was a nucleus at the center, but whatever was at the center pushed the alpha particle away from its path, which clearly means that whatever did this job must have been much heavier than alpha and would have, of course, the same charge, but the charge point is a separate point. So gold did not move or did not experience movement. It stayed in its own place. And although they both experience the same force, because if this is the gold nucleus and this is alpha particle coming close to it, the amount of force the alpha might be exerting on positive charge would be equal to the amount of force exerted by positive charge on the alpha particle. So this is basically Newton's third law, action reaction pair. Since the forces are same, gold nucleus should also be leaving its position, but it didn't, which means it has very high mass, it has very high inertia. Apart from the metallic bonding, definitely we agree that it is being held in place by metallic bonding, but at the time we need to respect the scientists who were doing this experiment. They didn't realize this, they didn't know that. So they settled that most of the mass of the atom is in the center in the nucleus. The second one is nucleus is positively charged. So again, we made this conclusion because alpha wouldn't be attracted, it would generally be repelled. And if it is being repelled, it means we knew that alpha is positive. It means that something at the center, whoever is doing that, should also be positively charged. That is how we came to this conclusion by the observation. A source contains radioactive isotope of strontium. This is decays by emission. Half-life is 29. Okay, fine. State the charge on the nucleus of the beta positive. What happens inside? What's the mechanism? So again, a memory-based question. A neutron changes to a proton, P11 plus, beta 0 minus 1. You see, this proton stays inside the nucleus and beta gets ejected out as beta radiation. It started when a neutron decided to disintegrate. A neutron disintegrates into proton and an electron, or electron is emitted out, proton stays inside. That is the mechanism of beta negative radiation. The initial mass of the isotope is 25 micrograms. He said the mass of strontium isotope decays in 87 years. How much of strontium are we going to lose? This is a tricky question. It's just a matter of wordplay. Please be advised, he's not asking you the mass of the daughter particle. He's asking you how much mass has decayed of the parent particle, which is strontium itself. But we go through the same procedure of decreasing its value half by half very easily and very straightforward. So we start with 25 micrograms of strontium element. Okay. Now, we need to understand how many times we need going to half the value. So we have half-life is 29. We're waiting for 87 years. So 87 years divided by 29, this comes out as 3 half-lives. We have to wait for 3 half-lives to make 87 years completely. So this will be divided by first time. We get 12.5 divided again by 2. We get 6.25 divided again by 2. We get 3.125 micrograms. Now, it begs the question, what is 3.125 micrograms of? This is actually the daughter. Sorry, this is actually the strontium itself. This is what strontium, or the amount of strontium that is left behind. All of the rest of the element has converted into the daughter particle. Now he wants to find out how much has decayed. That decayed. So it started with 25. Today, it's only 3.125. So I will have to take a subtraction or difference of 25 with 3.125. I'm left with 21.875 micrograms. Up to two significant figures, this will be 22. Now, does it make sense to round it up to 22? Yes, it does. Why? Because radioactive emission is random in nature. And the calculation that we're doing right now, these are just estimates. These are not going to be 100% accurate. It's quite possible that exactly after 29 years, when we check, this is actually 14 micrograms, or this is probably 10 micrograms, slightly more, slightly less than the actual calculated value. This is what randomness of the radioactive decay means. So yes, we can expect this to be, for the sake of mathematics, we did round it off. But can we expect this to be 22 in real life? Yes, we can. It shouldn't have to be, or it wouldn't have to be exactly 21.875 if we waited for 87 years, right? Question number 10. Now, to help with question number 10, I've added an image over here so that you can color this. So, opposite from the popular belief, this will be dark, because we are not able to see this the moon when it is directly between the sun and us. And if you come here, this will be partially lighted. This will be the dark portion. Over here, this will be the dark portion. Over here, this will be the dark portion. Again, I'm coloring the darker portions. And similarly, over here, this will be the dark portion, and this will be fully bright, and this will be the dark portion. So you can take a screenshot. I'm pausing the video at this point. Okay, so it says, where does the moon look like this? So it's very simple, very straightforward question. Nothing is left behind. So it could be A, could be E. Where there is a full moon, fully bright, is going to be G. State the approximate time taken. So this is again from memory. That is 1 month. But if you want to be really precise, it's actually 27 Earth days. That's how much time the moon takes. The average distance from the sun is this much. Be careful about the kilometers and the kilometers per hour. The average orbital speed. So this will be V equals to 2 pi r divided by t. I will leave the kilometers in as it is because the question requires it to be in kilometers per hour. So 1.5 into 10 raised to the power 8. Now, how much time do we have in hours per year? Because that's the amount of time taken. So 365 days multiplied by 24. I will leave this in hours because it's in kilometers per hours. When you calculate this, this comes out as 1.1 into 10 raised to the power 5 kilometers per hour. So 1.1 into 10 raised to the power 5. I don't have to worry about the unit in this question because it's already written here. And be advised, since this topic is new generally, they will be providing you with units, but soon they will start removing these units for you and you'll have to write them down yourself. The speed of light is this time taken. So it's a very straightforward question. Speed equals distance over time. 3 into 10 raised to the power 8. Distance is given to me as 1.5 into 10 raised to the power. Now this question, we have to be careful. So this is 10 raised to the power 8 kilometers. I need this to be in meters. So into 10 raised to the power 3 will be added in this, which will make this to be 10 raised to the power 11, I think. Yeah. So 1.5 10 raised to the power 11 divided by time t. This time t comes out as exactly 500 seconds. So we'll write down 500 seconds. Oh, sorry. Simple S would be the unit. Question number 11 says, state the condition required for protostar. Protostar is the initial initial state of the star formation. So the inward gravitational forces are still gathering the hydrogen from the clouds of dust in the universe, and they are being balanced by the outward explosion of the forces that are inside due to fusion. So basically, gravity is trying to pull the material of hydrogen in, and the explosion at the center, because of the fusion, is trying to pull or push everything out. This balance is being achieved or is being produced when this starts happening. The star is called protostar. Again, these are very initial stages of a star formation. Define the Hubble constant. So It is primarily v equals to h naught d, and they calculate this or define this as 1 over h naught generally as the life of the universe. But what is Hubble's constant? So it is the ratio of speed of receding, because if you make h the subject of the formula, this is what you get. So what is this v speed? What's the speed of? Is the speed of galaxy moving away from you. So speed of receding galaxy moving away from the Earth by the distance divided by the distance on the observer from the Earth. So this is the Earth where you're standing right now, and this is the galaxy that you're observing through a telescope. The distance between the galaxy and you is the d, and by what speed is this galaxy moving away from you? That is a Hubble's constant. The current estimate Hubble constant is 2.2 power minus 18. State the equation which gives an estimate for the age of the universe. So this is where we take the inverse and we actually find the age of the universe. Again, this is a classic repeated question. You can go to the book and read more about this nearing the end of the video. So the estimate of the age of the universe. So 1 divided by 2.2 into 10 raised to the power minus 18. There are other ways to estimate the age of the universe, but this is the closest one we have found for using the Hubble's constant. So when you do that, your answer comes out as 4.54 into 10 raised to the power 17 seconds. I have to be in seconds. So this will be 4.5 into 10 raised to the power 17, and this becomes generally 13.8 or 14 billion years. I hope you've learned something. That is all for today.